Hello everybody and welcome back. This is example 11.6 and we already did this in class, but we had a little bit of trouble with, and this was partly my fault as well, with the part B and C. We initially had some difficulty calculating the angle that the key or the fuzzy dice make with the horizontal, and part D is going to be asking, what if you have something that's heavier, like your keys? How is that angle going to compare to the angle of the fuzzy dice? And this is what we were trying to do here. We could have made a vector triangle, all right, or a vector diagram out of acceleration, all right. For, I should erase this. I'm going to make some. I'm going to write a little bit skinnier. For acceleration, we can make a vector triangle out of that. The acceleration that the entire car is experiencing is, first of all, the centripetal acceleration, which I think we found the centripetal acceleration of the whole car system to be 4.34 meters per second, because we had the velocity and we had the radius right there. Okay, but there's also the vertical acceleration that that each object is experiencing, but each object is experiencing that a little bit differently, or to a different degree. Here you have the dice that are being pulled down, all right, and held up by the string, or you might say the supporting force, or the supporting the vertical direction. The supporting is being applied by the string right there. For the car, what is supporting its vertical acceleration is the normal force. And so, either way, that acceleration that is creating that force is simply g, right there. So we could have found this angle theta by taking the inverse tangent of the opposite value, that is the centripetal acceleration, divided by the adjacent value, which is gravity. All right, but the one thing we tried to do in class, we tried to use forces to do this, and we can do that, but again, I'll take ownership of that. I made a mistake. We plugged in the wrong force and got a crazy angle. Let's do a force vector diagram down here at the bottom right here. All right, so vertically and kind of at an angle right here, this is going to be our fuzzy dice, okay, hanging from the rear view mirror. And let's just pretend that we don't know that angle right there, okay? But what are the forces? Well, this would be the downward force, or I should say really the force that's applied upwards by the string, or by the whatever is supporting the fuzzy dice. That upward force is going to be mg. That is the mass of, not the car, not the keys, not anything else, but the mass of the dice. Mass of the dice times gravity. That's going to be the upward force. The horizontal force that is going to be applied to that right there, which is actually kind of pulling it in, making it fly out because of inertia, is our mistake, and my mistake was calling that horizontal force the same force that's acting on the car. It's not acting on the car to keep this this dice at this angle. It's a force applied only to this dice, or this die right here. The force applied to the whole car takes into account the mass of the whole car. We don't have the mass of the whole car. We just have this die right here. So what we should have done is take this force. First of all, the acceleration in the horizontal is what? The centripetal acceleration, right? So the force would be the mass of the dice times the centripetal acceleration. That's the force that is created on the dice horizontally as a result of this acceleration. I mistakenly had us initially try to put in the force on the whole car, and that doesn't apply to this because this is just the dice right here. So this should work. You'll see that really this is the same proportions as that. It just has each side, that side is multiplied by the dice. This side is multiplied by the mass of the dice right there. It's the same proportion, so the angle should come out. The question is then, for part D, what is the angle for the keys? What is the angle for the keys? How does that compare? So this angle right here, if we use a force vector diagram or we use an acceleration vector diagram, in fact I should label this for force, that's that right there. All right, but what about for the keys? In fact, let me draw the keys in a little bit different color. No, I'll keep them blue. Let's say we have a greater mass, all right? So the keys are hanging from, I guess, a keychain or something like that. And I'll make the keys a bigger mass right there, all right? They're more massive, they're made of metal, and they're kind of swinging out to the side as well. It would make sense that being more massive, it would, or it might make sense that being more massive, it would be a different angle, but we're going to find that the angle is actually the same. Why? Because every part of the car, whether it's the keys, the dice, the car itself, is experiencing the same centripetal acceleration and experiencing the same vertical acceleration, which is gravity. So if we simply multiply each of the accelerations by the mass now of the dice, we'll call the mass big M right here and big M right here, we should be able to say the force, the centripetal force in that direction is the mass of the dice by the centripetal acceleration. The vertical force right here, really the supporting force of the string or the lanyard or whatever your keys are on, is mass of the dice times G right here. Nothing is really changing. Just the proportions are not changing, the values are. But look, we still have this G right here multiplied by M. This centripetal acceleration here multiplied by M right there. And so as a result, this angle, theta, is going to be the same as it is right here, as it is right here. It's all the same thing. So as long as we design a vector triangle, because really this angled force right here is applying or acceleration is applying a component in the horizontal and the vertical. If we make a vector triangle that has basically all the same types of units on all sides, we should find that that angle theta is going to be the same regardless of what's hanging on the end of it. That's why if you ever see those amusement park rides where they look kind of like that, and there's a thing like a big T that swings around, and you've got swings, and people of all shapes and sizes are on the swings, and they get whipped around in a circle like that. The designers of the ride don't need to worry about how big the person is who is on the end of that swing right there. All they have to worry about is it going fast enough so that you don't fling the people off and break the chains. All right? Every person, regardless of their mass, is going to have the same angle with the horizontal. Actually, I shouldn't say that because a lot of times they are closer to the inside and closer to the outside. But if everybody is at the same distance, the same radius from the center, they're all experiencing the same what? The same centripetal acceleration. All right? Even though they have different masses, we multiply them all by the same centripetal acceleration and they're all experiencing the same gravity, that angle for each person, assuming they're all the same distance from the center, is always going to be the same. I hope that helps. I apologize for kind of misleading you a little bit. We had the wrong force in the horizontal right here. But that's our explanation, and I hope that sorts things out for you. So if you have any questions, please make sure you see me during my office hours, or if you can catch me when I have a study hall. But otherwise, thanks for following along, and I'll see you on the next one.